Rates of change. Let's take a look at this graph, which shows the position or the distance a person had traveled in miles over the course of 3 hours. And let's say at t equals 0, they were 0 miles away from their house. So if a person drove 120 miles in 3 hours, we know that the average speed of the person was 40 miles per hour. Now, did that person go exactly 40 miles per hour over the entire 3-hour period? Well, probably not, and certainly in the graph we see that he did not. But let's take a look at one other thing. What if we found the slope of the line between t equals 0 and t equals 3? We know that the slope is the change in y over the change in x, in this case t, and that gives us 40, which of course is not a coincidence. So when you see slope, I want you to think speed, or more generally, I want you to think a rate of change. So the slope of a graph is going to tell us how fast something is changing. Now, if we do it over a long interval like we did here when we did 0 to 3, we get an average rate of change. So one of the goals in calculus is how can we find an instantaneous rate of change? For example, if I look back at this graph over here, at what instant in time do you think the person was going the fastest? How about right there? Do you think the person was going the fastest at t equals 2? Probably not. Now, in your head, I bet you're thinking maybe somewhere over here. And you're thinking it because the slope of the graph is the steepest right around over there. So how can we find the slope of the graph at a point when a slope is always between 2 points? Let's go through some notation. Consider our function f of x. Our goal is to find the slope at that one point. And we're going to do it in the following manner. We're going to start by getting an approximation of the slope of that point. That is, we'll take the slope between a point that's kind of close but not too close. And we'll call this point over here something. What should we call it? Well, let's talk about the distance between the points as being h. So very often in calculus, when you see h, think delta x. So if this point is x, and the distance between this point and this one is h, then that point must be x plus h. Let's get some y values over here. At this x value, that y is f of x. At this point over here corresponds with x plus h, then the y value is f of x plus h. And then the slope between the 2 points is y2 minus y1 over x2 minus x1. And if we were to simplify that, we would get our slope is f of x plus h minus f of x all over h. Once again, I want you to think h is delta x. So when you see this over here, going forward in calculus, I want you to think a slope. Now, this slope gives the average rate of change between the 2 points. And remember that our goal is to find the slope at this point. Can you think of a way to get a better approximation of the slope at that point? Because what we have right here, our average rate of change, is an approximation. And it could be equal, but it's probably not equal to the instantaneous rate of change. So how can we get a better approximation? If you thought make h smaller, that was a really good thought. Now, if I take this slope, is that the slope at my point? Well, no, but it's probably closer. Certainly looks like it's closer to the actual slope. So how can we get an even better slope? In fact, how can we get the slope at that point? What if we keep squeezing h down to 0? So that the points are so close, they're basically the same point. That is, what if we find the limit as h goes to 0, or delta x goes to 0, of our slope? F of x plus h minus f of x all over h. When we do this, we get the instantaneous rate of change. So in calculus, when you see this here, this is the way I want you to think about this. This right part is a slope. And our limit is saying, let's squeeze those points so close together that they're basically 1 point. In the next video, we will see what this instantaneous rate of change really is.